Howdy. The point of this video is to talk about stereoisomers. Now there are different ways that we can make a polymer, a long macromolecule, by arranging different sequences of repeat units. However, there are differences within the repeat units themselves, and that is different ways that we can arrange side groups onto a repeat unit that are not alike. And by arranging different series of these repeat units that have side groups in different positions, we get what are called stereoisomers. So let's think about these in 2 dimensions, first of all, because we need to figure out a way to represent them on the written page, right? And so you can see this one of 2 ways. You can see a geometric representation, and this cone represents side groups that are coming out, and the dashes represent side groups that are going back. Or we could kind of all smush it on a single plane and show it in this sort of fashion. However, it's still a little difficult to see in 2 dimensions. So we're going to think about models shortly. Now, stereoisomers can take 3 different fashions. We can have isotactic, atactic, or syndiotactic. Iso means the same. And so these are repeat units that the configuration of the side groups is the same within each repeat unit. So we see this R group. R is a shorthand notation for some side group. Is in this position, it's in the same position in each individual repeat unit. And so just to be clear, a repeat unit in this polymer would be something like that. And you can see the same thing when we write it in the flattened 2D representation here. This R group is in the same position. So let's see what this looks like in 3 dimensions. Our repeat unit here is a very simple repeat unit. We have 2 carbons. We have 3 side groups that are the same. Maybe this is a hydrogen atom. And we have a 4th side group that's unique. This could be a fluorine atom. This could be a propyl group, CH3. It could be an aromatic benzene ring. But for the point of this, this group is different from these 3 side groups. So there are 2 ways that this repeat unit could be arranged. There's this fashion, or I could switch the position of these 2 side groups. Now, this is different because even though we can rotate around this single bond, this orientation was not the same as that original orientation, right? Because they have this tetrahedral configuration. And so you can see that if we go back to the original structure, this side group is repeated. The orientation of this side group, rather, is repeated within each repeat unit within the polymer chain. Now, if I start randomly switching the orders, maybe I switch that one, maybe I have a couple that are the same, or maybe this one down here is switched as well. You can see that this is now a different configuration, right? So there's no way to rotate this such that it's the same as before, right? Even if I rotate down here, this is unique. This is a different position. And I can't get back to that original configuration just by rotating the bond. So what I have now is I have the syndiotactic, or I'm sorry, I have the atactic, the random configuration, right? So if I was going to denote this by some simple terms, for example, A, B, A, B, right? The configuration of these 2 repeat units is unique from the configuration of all the others. So this is atactic, random. Now we also have syndiotactic, which means alternating. And so in this case, we would alternate A, B, A, B, A, B, right? The important thing here is that even though all I did was switch just these 2 side groups, there's no way to get this side group be equivalent to this side group just by rotating through the single bonds. And that is what stereoisomers are all about.